All right, folks. Showtime.
Electricity is at work all around us. In our offices, our cities, our schools, parks, and homes, and in nature.
Wow, I can't believe that Benjamin Franklin was out in a storm like this just to do experiments with electricity. I'm surprised he didn't get hurt.
You're right. Electricity can be dangerous if not used properly, but it can also be our friend.
Whoa, who said that? You're Benjamin Franklin. I have to study by you. You're part of my homework.
Me?
Yes, you're one of the greatest contributors to the study of electricity. Hey, maybe you could help me with my homework. I need an adult to help with the experiments.
Well, why not? Maybe I could learn something too. Well, electricity has certainly come a long way since I first experimented with it.
Okay, first assignment. Describe electricity.
Electricity is a form of energy. It can give us light and heat, and it can produce a force that can make things move.
That lightning sure made me move. What is lightning anyway?
Lightning is a form of electricity that exists in nature. In my kite experiment, I proved that it is an electrical current. The moving energy, or current, jumps between two clouds, or within the same cloud, and sometimes it flows between the clouds and the earth.
But what causes it?
A simple explanation is that the heat and light we call lightning is really just a giant spark. You can experience a smaller version of the same kind of electrical energy by rubbing something, like your cat, and then touching something metallic, like a doorknob.
Oh, I know that. That's static electricity. There's a cool experiment in my book about static electricity. Shall we do it?
It sounds like fun.
Here's a balloon, Ben. Now try sticking it to the wall.
Doesn't stick.
Rub it in one direction and try sticking it to the wall again. It sticks.
You could pick up bits of paper with it, too.
Whoa, that's cool.
This next experiment is almost the same. Let's charge up these balloons on the cloth and then hang them on this rod.
They're pushing apart from each other. Will they push or pull anything else?
There's another experiment we can do to find out.
What do we need?
Some running water and another balloon. First, we need something to catch the water.
The pot.
Next, I'll hold the charged balloon next to the stream of water.
Hey, the water moved. Electricity really does move things. It's like a magnet.
Did you know that things can either have a positive, negative, or neutral charge? Mostly things are neutral. They don't pull or push each other. Those balloons, once we've rubbed them, have a negative charge. It's like we rubbed something away, and now it's trying to pull it back.
That's what makes them attract other things?
The push or pull force is known as a positive or negative charge, a minus or a plus. Things with a negative charge repel other negatively charged things. Things that have like or similar charges push each other away. They repel each other. Things that have unlike charges pull towards each other. They attract each other.
That's like a magnet.
That's right. Electrical charges are related to magnetism, but they're not exactly the same. Electrical attraction and repulsion comes from electrical charges. The magnetic properties of electricity can make things move.
Electricity does a lot of work for us. It gives us light, heat, and power, like we said. But it also gives us communication, like the TV, the radio, the telephone, and computers. I don't know what we would do without electricity.
What happened? Do you have a candle?
No, but I think somewhere in here I've got a flashlight.
My goodness.
The lights went off. The radio went off. I think the lightning may have struck the power lines.
What do you mean by power lines?
The power lines carry the electricity to our house.
But where does it come from?
It comes from a power station, where they start the electric charge flowing through special wires that bring it right inside. We plug into the power source with cords from our appliances, and that is how we get our electrical power.
So, something stopped the flow of electricity through the wires.
But it never stops for long. Someone will be out there repairing the damage soon.
Well, in the meantime, perhaps we could do another experiment.
First, let's put the flashlight over here.
Would you like to see how electricity flows?
That's a good place to start.
Well, the first thing we need is a source of power that we can safely experiment with.
Wow! The battery.
Next, we need a light, a switch, and a conductor.
What do you mean by a conductor?
Well, electricity won't flow through just anything. A conductor is a material that allows electricity to flow through it, like this copper wire. Now, let's attach one end of the copper wire to the battery and the other end to the lamp.
Nothing happens.
That's because we need to complete the circuit.
Oh, right! So when we press this switch, the circuit is complete, and the electricity is allowed to flow.
This is a simple circuit. Ah! Just as we've completed our circuit, someone has completed the circuit to the house.
We're using a metal wire here as our conductor. Do you think we could use this piece of string?
Well, let's find out.
Nope.
What about that piece of paper?
Let's try. Nope. In my class at school, we learned that something that doesn't conduct electricity very well is called an insulator.
That's right. An insulator prevents the flow of electricity. The copper wire is insulated on the outside, except here at the ends where we need it to touch the battery. Inside the insulation, the copper wire is carrying the electricity. A series circuit is connected in one continuous line. You can add more batteries to increase the power. You can add more lights as well. If one light goes out, the circuit will be broken. There is another kind of circuit called a parallel circuit. Parallel means the wires run side by side. In this parallel circuit, each power source and each light bulb is attached to the circuit in a separate line. You can remove one of the lights without breaking the circuit. You don't get more power if you add more batteries, but the batteries will last longer. Now, what's your next homework assignment?
Describe how electricity is related to magnetism.
Ah, well, I just happen to have a little demonstration of that right here in my book. Notice the metal bar with the coils wrapped around it and the wires connected to the battery. Now, this metal bar normally would not be magnetic until we apply an electric current, and then it becomes a magnet, an electromagnet.
It picks up these paper clips.
Some magnets, such as this bar magnet, are permanently magnetic. They always have magnetism. An electromagnet is only magnetic when you apply an electric current. Now, let's try one more little experiment. Let's place the bar magnet next to the electromagnet.
So when I push the switch, electricity flows through the electromagnet and they push each other apart. just like the experiment with the balloons.
That's right. Now, let's take a look at two more of your modern inventions that use this same idea, the telegraph and the telephone. Before the telephone was invented, the best way to communicate over long distance was through the telegraph. This is how a telegraph works. It looks a lot like the simple circuit that we made. It has a switch called a key and a sounder, that's what makes the noise, and a source of electrical power. The coils wrapped around the metal posts of the sounder are...
I know. They're electromagnets.
Right. When the key is pressed, you can send messages between the two sounders. A telephone works with an electromagnet, but it also has a permanent magnet. The permanent magnet holds a thin metal disc called a diaphragm. When you listen, a voice comes over the telephone receiver as an electric current. The electromagnet responds to the current and moves the diaphragm in the exact pattern of the voice. When you talk, another diaphragm creates an electrical current that matches the pattern of your voice and sends it over the telephone wires to the other person.
Hey, every time I talk on the telephone to my friends, I'm using an electromagnet.
That's right. Now, any more homework?
Yes, I need to explain how a generator works, like the one that brings electricity to our house.
Well, a generator doesn't create electricity. It uses some other form of energy, such as the force of water rushing over a dam, and changes it into electricity. Look at this diagram of a simple generator. Tell me what you see.
I see a conductor, the wire loop, and the U-shaped magnet. In this case, the wire loop is turning inside of the magnet.
A generator uses a permanent magnet. The magnet creates a push and pull against the wire and sends the electric current through the circuit. The water rushing over the dam turns the conductor wire inside the magnet and an electric force is created.
It looks a little bit like a motor.
Somewhere in my book, in fact, I think I have a simple motor.
Wow!
You see the electromagnet, the circuit, and the power supply.
I recognize all of those things. Let's see if it works.
When current is supplied to the coil, it becomes like an electromagnet, which works with the permanent magnet below it, causing the coil to spin.
I've learned a lot from you.
I've learned a lot too. Let's review what we've learned. Electricity is a form of energy that can give us light, heat, and make things move. Lightning and static electricity exist in nature and are caused by an electric current jumping from one thing to another. One characteristic of electricity is that it can have a positive or negative charge. Unlike charges attract, and like charges repel. Some things, like metals, carry electricity and are called conductors. Other things, like string and paper, do not carry electric charges well and are called insulators. Electric charges flow through conductors in a circle or circuit. Electricity is related to magnetism. The telegraph, telephone, and generator use electromagnets. Electricity is an important part of our everyday life.
Andrew, did you get your homework done?
Yeah, it's all done, Dad.
Well, put your book away and get ready for bed.
Okay, Dad. Good night, Ben. Whoa.